Any questions about anything? Last time or anything? Well, last time I was in the middle of computing this integral using a famous technique about using the residue theorem on a contour. And this is a typical contour that comes up when you have a root function or a log function in the real integral. And we'll see why it's the thing to do in a second. So I've got this contour. I call this a Pac-Man contour because it looks like it has a mouth on the right-hand side. That's to let the branch cut through. And I have that top one T and the bottom one B there. I'm going to let the alpha go to 0. And that integral along the top part is going to be exactly the integral we want when we look, because the theta in the branch of the log and square root function goes to 0, and in the limit, when alpha is 0, that theta would be 0, and that would give me the real integral I want. And interesting, when I come around to the other side on the bottom there, B, the theta would be going to 2 pi. And so as I let that alpha angle, the minus alpha, go to 0, it turns out that I don't get something that cancels the top. I get something different. It's actually something times the top integral. And so they don't cancel, and that's what is going to allow me to calculate the integral I want. So I'm applying the residue theorem on that curve gamma, which is a simple closed curve, and there's a single pole inside. My f of z is 1 over z to the 1/2, and I've defined that branch last time, times z plus 1 in the denominator. So when z is equal to minus 1, it has a simple pole at that point. And last time, let's see, the branches, I'm using that branch that goes out the real axis there. Call that log 0 because the angle goes from 0 to 0 plus 2 pi. And so there is the definition of the function, z to the 1/2. And last time I calculated that residue, it's an easy one because it's a quotient of things. The function on the top is 1, and the function on the bottom is has a simple 0 at 1. And so you can either use the formula or just do it from first principles. And last time we got that residue is 1 over I. So I'll do that again. Let's see. Then I thought I'd do the easy estimates next. The integrals along the circular parts tend to 0 as I let r go to infinity and epsilon go to 0. And that was to estimate those, I used the fact that the modulus of a square root is the modulus of the z to the 1/2. So that allows me to estimate that thing on the circular parts quite easily. So let's see, I demonstrated that last time. Another way you can see that is if you had a square root, then you would know that, let's say we know that w squared is equal to z. And then w is a square root of z. And if you take the modulus, you would get this, and this is the modulus of w squared. And so you see that the modulus of w is the modulus of z to the 1/2. So you could do it that way too if you prefer, because you know that square roots, when you square them, are the number. So, or could do that. Okay, so I'll do the big R first. when I estimate that integral, I have to find the maximum of this function on the circle. And the length is actually less than or equal to 2 pi r. It's slightly shorter than a whole circle, so it's actually less than 2 pi r. So that's a correct estimate. And so let's see, on the circle, the modulus of the z to the 1/2 would be r to the 1/2. And I claim I'm using the denominator estimate to get the 1 over z plus 1 thing to be bounded by 1 over r minus 1 when r is bigger than 1. And that's going to go to 0 when I put the 2 pi r back in here. I should put it back in here, times 2 pi r that goes to 0 as r goes to infinity. So let's see, I was at this point where I was going to explain why I needed that denominator estimate. It's a very common error to put something like r plus 1 in that spot where I have the r minus 1. But because that's in the denominator, I need the denominator estimate. I need the modulus of z plus 1 to be bigger than or equal to something. And so let's see, on the outer circle, when I use the denominator estimate, modulus of z plus 1 would be greater than or equal to the absolute value of the modulus of z minus the modulus of 1. And so on the outer circle, that would be equal to r minus 1 when r is bigger than 1. But on the inner circle, when the epsilon is small, that thing would be 1 minus epsilon. When 0 is less than epsilon is less than 1. So, two different things there. And so the estimates are totally different, but they're going to both go to 0. So I did the outer one. That was pretty straightforward. Now let's do the inner one. So let's see the c integral around c sub epsilon, plus or minus, it doesn't matter. I'm going to be going around clockwise, but I'll get the same estimate. So that'll be less than or equal to that max, and this time the max will be, let's see, epsilon to the 1/2. So that looks like that's something small in the denominator. That could be bad. But then it gets multiplied by not epsilon minus 1, but 1 minus epsilon. And then I have the length of the curve. Well, the length is slightly less than 2 pi epsilon. So 2 pi epsilon is an upper bound. And now the thing happens that because of that epsilon in the numerator, and the 1 minus epsilon is tending to 1, so in fact the whole thing looks like, let's see, this is equal to 2 pi epsilon to the 1/2 when I cancel, and on the bottom I have 1 minus epsilon. And that's when epsilon is less than 1. And that goes to 0 as epsilon goes to 0. Okay, so that's good. Now I'm going to mess around with the top and the bottom part. So next, let's think about the top curve. Well, the top curve, remember, I want to parameterize it by something. So, let's see. Let me think about the top curve. I made it green, didn't I? It goes out like this. And I want it to go this direction. This is the point r e to the I alpha. And it starts at the point epsilon e to the I alpha. So if you ask yourself how you might parameterize that curve, it would be, let's see, and so this angle here, here's 0, maybe farther over. And this angle is alpha. Okay, so think about it. It's the t, I want to go from epsilon to r in my integral. And so the natural way to parameterize this thing, so I'm asking what the heck the z of t is. The z of t ought to be t times e to the I alpha, as t ranges from epsilon to r. Then the integral along t of f of z dz would be the integral as t goes from epsilon to r, and f of z would be, let's see, t e to the I alpha to the 1/2 times t e to the I alpha plus 1. And let's see, if I have this z prime, then my z prime of t here is e to the I alpha. So my z prime of t dt would be e to the I alpha dt. This is z prime of t dt in the definition of the complex integral. Well, I claim this is going to tend, as I let alpha go to 0, this is going to tend to the integral I want. Let's see, what's the, this is the integral from epsilon to r. Okay, t to the I to the alpha to the 1/2, that would be 1 over e to the 1/2 natural log of t e to the I alpha, which is going to be log of t, plus the angle of that thing is alpha. And so remember, the angle's going from 0 to 2 pi. So there it's exactly alpha. And then I have t to the e to the I alpha plus 1. I can pull this e to the I alpha out front if I want. And I get a dt here. And this is the interesting thing to look at, is this part right here. That's going to be e to the 1/2 natural log of t times e to the 1/2 e to the I alpha over 2. And t to the e to the 1/2 t is the square root of t. Okay, and now if you stare at that for a second and realize, if I let the alpha go to 0 now, everything in there slides in continuously and nicely to, so this is the moment we realize, aha, let's let alpha go to 0, decrease to 0 from above. Then the e to the I alpha tends to 0. I mean, tends to 1, as alpha tends to 0. And so does the e to the I alpha over 2. And so we see that the integral along t, all those e to the I alphas are going to tend to 1. and they do so in a nice uniform manner. And what I'm left with is exactly the integral I want. So what we see is that the integral along t of f dz tends to the integral from epsilon to r of 1 over the square root. This is the thing we want. Okay. Now it's time to do the same thing exactly for the bottom one. Question about that? That's an important, yeah.
Earlier, I think a little bit upwards. And the denominator, it's what do you have in that log? What do you have also in the I alpha in the log?
Right, that's the I argument. And the argument of t e to the I alpha is alpha. Yeah, so that's the theta. That's the important part. Okay. We want that. So next, we do the bottom part. And let's see, the bottom part, remember I had a minus b, but the b, if I was going the other way, it would be z of t equals t e to the minus I alpha. That would go starting at the corner closest to the origin and go out. What I'm really going to use is minus b in the end, but this is easier to parameterize. So it's t e to the minus ia as t ranges from epsilon to capital R. And I do that same routine, and I'll get the integral along b of f dz would be equal to the integral, let's see, this time an e to the minus I alpha would come out. Oh, no, it wouldn't. T e to the minus I alpha. Yeah, that would come out, because that's that comes from the parametrization. But then I'd get the integral from epsilon to r, and here I'd get 1 over, let's see, this would be e to the 1/2. This would still be the log of t. But then this time, let's think about what the angle I get. I times the argument. And if you think about, I should have drawn my picture, I'll do it here. Here's my real line. And now I'm using this is b. I'm going to use minus b. Okay, and this is the this angle here is now minus alpha. And so if you think about it, remember I had theta going to 0 along the top. And theta going to 2 pi along the top, the other side. And so the angle in the log function would be 2 pi minus alpha. Something different than the other side. And that's important, otherwise we'd get a big fat 0 when we add them up and cancel them. Okay, and then we also get t e to the minus I alpha plus 1 dt. And now if you think about what happens as alpha goes to 0, that e to the minus I alpha would tend to 1 in front, and it would tend to 1 in the other places. But what you get differently when you do this is as alpha goes to 0, you get that the integral along b of f dz tends to integral from epsilon to r, and here we'd get, on the bottom, t to the 1/2 And then we get here e to the I over 2, let's see, e to the I times 1/2 times 2 pi. Yeah, so when that red stuff, as the alpha goes to 0, that would just be an I 2 pi. And I've got 1/2 times I 2 pi when I put that through. And let's see, this part would just be t plus 1. And I'd have a dt left. And let's see, that's a e to the I pi. E to the I pi is just minus 1. So it's minus the thing I want. So this is equal to minus the thing I want, which is the integral from epsilon to r of 1 over the square root of t times t plus 1 dt. And so the integral from the one I really want is minus that. Integral along minus b is equal to minus the integral along b. And so integral along minus b is going to be plus that. So the limit as alpha goes to 0 of the integral along minus b of f dz is equal to the integral from epsilon to r square root of t plus 1 dt. And I want that. And fortunately, it doesn't cancel. It would be a real bummer if that canceled the first thing I wanted. That would mean I made some bad choices. Okay, so now I'm done. I can put it all together. But yeah, I have to be a little bit clever here. So finally, it's important what order I do this in. Finally, step 1, let the alpha go to 0. Okay, remember I've got let's see, so finally what am I doing? I'm going to add up the integral around this outer circle plus the integral along minus b plus the integral along plus top plus the integral, let's see, is this going to go around minus b, oh, this one, c sub epsilon, c sub minus epsilon would be next, and then finally c sub top, integral along the top, f dz, that's equal to 2 pi I times 1 over I was my residue. So step 1, let epsilon go to 0, let alpha go to 0, then that's going to go to integral along c sub r, and this is going to, the bottom, remember, is going to go to the integral from 0 to, no, epsilon to r, epsilon to, so the bottom and the top are going to both go to the integral I want. So those are going to be 2 times the integral I want. So this one's going to go to want. This one's also going to go to the thing I want. So I get 2 times the thing I want. Plus the integral along c sub r, c sub minus c sub epsilon of f dz. 2 pi I times 1 over I is just 2 pi. Okay, step 1 now is let epsilon go to 0. Step 2, rather. Step 2, after you let alpha go to 0, Now let epsilon go to 0. Goes down to 0. And then that last integral would tend to 0. And so finally we get, so that's step 2. Step 3, let r go to infinity. And when you put it all together, you get 0 plus 2 times the integral you want plus 0 equals 2 pi. So we conclude that the integral we want, that was the integral from 0 to infinity of 1 over square root of t times t plus 1 dt is equal to pi. That's the right answer. Yes. Okay, I guess that was kind of hairy, but everything was, I guess the only thing you had to really think carefully about is letting alpha go to 0. Questions about that? That's the way I like to do it, because I like to think of that Pac-Man and I like to think of closing the mouth. But some books take, including our book, they do this to avoid thinking like that. Here's what they do. They take a contour that has a big circle and a little circle about 0, and then has a cut like this, and we go around, we go this way on the top and this way on the bottom. Let's see, and then we got that pole at -1. Okay, and so this would have a circle part on the outside, C sub r, and a circle part on the inner side, inside, going clockwise. That would be the minus C sub epsilon. Okay, and we're going to take cuts going, that's my most important cut right there. And a typical thing to do next would be to take a cut here and a cut here. Okay, we're going clockwise in those. And let's see, I wanted to counterclockwise contours, so I'll go this way and this way. Then I'll go this way and this way. There, I think I'm almost done. Going this way. Those are all counterclockwise now. And so here's what I'm going to do. I want my theta to be going to 0 from this side. And I want my theta to be going to 2 pi from this side. Okay. So here's I'm going to do something. I'm going to cross out these branch cuts in a second. I'm going to add up so add up the counterclockwise integrals along the simple closed curves. Okay, when you add them up, I'm gonna use different branches in different U's. Carefully choose the branch. Carefully chosen branches. Of log. Okay, so in the first one, I'm going to make my branch cut. Oh, how about go out like this? That's in the first quadrant there. I'll take a branch cut like that. Then I want my angle to be 0 here, so it would be 0 here, and it'd be like, what angle is this? this would be theta equals, what is that, 3 pi over 4 maybe. Okay. So, and I'd use the Cauchy theorem in that one. This is the Cauchy theorem one, because there's no singularity in there. So that integral would be 0. Then when I do the next one, I want my angle to go from 3 pi over 4 to, how about 5 pi over 4. And I want those angles to agree along my cut, my first cut. And so let's say then I could take my branch cut to go out the positive real axis again for that second region. But on that region, then my angle would go from 3 pi over 4 to 5 pi over 4. And since they agree there, it's going to cancel. So that this one's going to give me a cancellation. If I choose the branch to agree there. So those are actually going to cancel and go away. All right? And I take this branch that goes from 0 to 2 pi to do that. And that one I don't use the Cauchy theorem. I use the residue theorem. Okay. And on the next one, I take a branch. Let's see, I might take my branch going out like that. And my angle would be 5 pi over 4 there and go to 2 pi there. All right. And that way I get cancellation along this cut. Cancellation of these cuts. Okay, so that's going to go away. And then finally in this last one, I would take a branch. I could take a branch that goes out this way for the last one. And then my angle would go from 5 pi over 4 to 2 pi there. And that would make that branch cut cancel, that second branch cut cancel. But it's not going to cancel the last one, the first one on the positive real axis. Those don't cancel. And when you add them up, so this one's going to be a Cauchy theorem because there's no singularity inside. When you add them up, you get the same thing you do at the alpha go to 0 stage. Add up, you get the residue theorem, but in a new form. Let's see. We had this picture that I started with. The contour was this. I had a pole at -1. And then I have this branch cut here that goes like this and like that. And when you add up the integral going around that closed Pac-Man mouth, you'll have a theta equals 0 on the top half and a theta equals 2 pi on the bottom half, and so they don't cancel. And get a residue-like theorem for this. The thing that's weird is that that path gets covered twice. So you start out going along the top of the mouth, and then the bottom, you go the other way along the bottom of the mouth. And you use different limits for the branches there. So to avoid thinking about limits, books cut it up into 3 pieces and use different branches in each piece. And they note that they get cancellation along the cuts where they were careful to glue it together, but the one where they couldn't glue it together, when they get around all the way 2 pi, they have to use a different branch on the other side than the top side. It leads to exactly the same conclusion. I'll put this residue theorem in quotes because it's not the standard residue theorem because of that double crossing of that red cut. Makes sense? I don't know which way you prefer. It took me more scribbling and talking to describe the book's method. But the closing the Pac-Man mouth is, you have to think about limits carefully. It's not a bad thing to do. Let's see. The next thing I want to do is a really fun example of a really famous integral using this technique. And it's the integral from minus infinity to infinity of sine x over x dx is equal to, you won't believe it, pi. That integral comes up in optics. And if you ever looked about the parallel slit interference of light, it comes up there also. In a key way. And every now and then you actually need to know the exact value of this integral, especially if you study Fourier series. That's a famous integral, and it's a famous integral from freshman calculus too, because it's not absolutely integrable. It's conditionally integrable. So this is it's famous. This thing is not absolutely integrable. But it is conditionally convergent. And that's the word we used in freshman calculus. But conditionally convergent. And let's see why. Sine x over x, famous limit at 0 is 1. And so if I graph it, it's 1 at 0, be 0 at pi over 2, and then it wiggles. And the bumps get smaller and smaller. So it starts out at 1. This would be a biggish bump, and then it gets smaller and smaller. Maybe that's too small. Big bump. I'll make a bigger bump here. Why can't I do this? Sorry. This is pi over 2, and then it goes smaller, smaller. Now this is that? Okay, it's still wrong. They're getting smaller. Okay, here's something I can do here that I can't do. I'm going to copy that. Control copy, Control E. Now I'm going to turn it inside out. That is a symmetric function. Okay, so why does this thing converge? It's because these areas here starting here at least, this area is bigger than the next area, is bigger than the next area. And they're alternating in sign. And so it's the alternating series test that shows you that that sum converges. So the alternating series test that you learn in freshman calculus, those areas of the humps are decreasing. Some of the humps are above the axis and some are below. Areas of the humps decreasing. And they tend to zero. They decrease to zero, and they're alternating. So of course they're going to add up to alternating sign. So the limit as r goes to infinity, for example, the right side, integral from 0 to r of sine t over t dt converges. And that limit exists. But let's think about estimating the I'm going to think about estimating let's think about but I want to think carefully about why that integral is not absolutely convergent. So I'll be out here someplace far away, n pi and n plus 1 pi. Sine vanishes at multiples of pi. So I'll take the absolute value of sine t, and that's just one hump of the sine curve. So this is the graph of sine of t right here. And when you calculate the area under one hump of a sine curve, you get cosine something minus cosine one end minus cosine of the other end. And that would be, cosine is 1 at those points, or minus 1. So it's going to turn out to be 1 minus minus 1, which is 2. That area is equal to 2. Okay. And so now I think about sine of t over t. Let's see, I would have t, I have n pi is less than t, or less than or equal to, is less than or equal to n plus 1 pi. So I claim that sine of t over n plus 1 pi would be less than or equal to sine of t over t over t, and that's less than or equal to absolute sine of t over n pi on that interval. And so if I integrate, put this in a box maybe, integrate from n pi to n plus 1 pi, when you integrate absolute sine of t, you get the area of that hump. So you get 2 over n plus 1 pi is less than or equal to the integral from n pi to n plus 1 pi the absolute value of this thing dt, and the other side, the right hand side, the area of that hump is 2, and you get 2 over n pi. Okay, so I can compare the sum of those integrals to the harmonic sequence. And so the integral from 0 to infinity goes to, so we see that this one shows that that integral goes to infinity. So integral from 0 to n plus 1 to an, because those are all bigger than that, because the harmonic sequence diverges. Summation 1 over n going from 1 to infinity, is the famous harmonic sequence that diverges. And this, the right-hand side just shows it goes to 0 at exactly the same rate that the, it goes, not goes to 0, it goes to infinity. Goes to infinity exactly the same rate. The rate is the same as the rate that the harmonic sequence diverges. So rate is the same as the divergence of the famous harmonic sequence. Or what is it, harmonic series? 1 over n is the harmonic sequence. The sum of it is the harmonic series. Okay. Yeah.
When you say the integral from 0 to r goes to infinity, you mean the integral from 0 to r of sine t over t?
Right. The absolute value. So the integral from 0 to r of absolute sine t over t. So it's not absolutely integrable. Goes to infinity. As r goes to infinity. Same thing happens on both ends. So it's kind of a interesting example. Kind of running out of time for today. So let me tell you what the plan is to calculate this integral. So far I've been using pretty simple contours, namely d's. But now I got to take a d with a bite out of it. I'm going to go around a CR like this. I'm going to have a left straight line piece. This is going to be minus epsilon. This is plus epsilon. This is plus r. This is minus r. And I'm going to have I'll call this L1 and L2. And this is going to be clockwise. That's going to be my contour. And you might think, oh, I should take sine of z over z. Well, sine of z goes absolutely bonkers on the big circle. It kind of has a very similar nasty singularity that e to the 1 over z had at 0. Sine of z is that bad out along the big circle, because it's think of it like a 1 over z when z is small. So you'd very quickly realize, oh my gosh, that integral is horrific and goes totally berserk. And I can't make it go to 0. But the f of z we need here, we get something, it turns out, if we take e to the iz over z. Because the real part along the real line there would be cosine t plus I sine t. And so the integrals along the lines are going to be relevant to what we want. And it turns out that the integrals along the circles we can deal with. The integral along the outer circle is going to go to 0, and the integral along this small circle is going to go to a number. Otherwise, we'd use Cauchy theorem and get 0, which wouldn't give us anything. Anyway, I'll go through the details next time. It's a very famous application of all this complex analysis to a pretty interesting integral. Any last minute questions about anything? Homework 9 is now on the home page. Okay.